60 years of human spaceflight. When you say that, it just sounds incredible. Starting from Alan Shepard's first 15-minute Mercury flight, through Gemini, through Apollo and the lunar landings, through Skylab, Apollo Soyuz, 135 space shuttle flights, Shuttle Mir, ISS, and the Commercial Crew Program, one element and one challenge has always been the same, and that's the human. And that's what we're here to talk about today. How do we take care of that person? How do we ensure their health, performance, and their very survival in the harshest of all environments, especially when they are operating vehicles that are uniquely designed to both support and protect. However, but in doing so, they contain their own unique hazards as well.
Thank you, John. Each of these individuals is very distinguished in their own right, but importantly have worked as part of the team for human health and performance with its various names over the years of 60 years. Today we're going to hear some of their stories and contributions through eras such as Gemini, Apollo, Skylab, Shuttle, Commercial Crew, and the International Space Station programs. And then we'll hear how different perspectives from both operations, research, and engineering have contributed to where we are today and a look forward towards the future. So let's get this conversation started. Bill, it is such a privilege to have you with us today. Absolute privilege for you to be at NASA Johnson Space Center today. There were so many unknowns sending humans into space during Mercury, Gemini, and Apollo eras. Flight surgeons were really pioneers in understanding all of these unknowns. Thinking back, how did your role as an operational flight surgeon help enable human spaceflight?
Well, a very important part of my job was conducting pre-flight and post-flight medical exams and tests along with a team of clinical investigators. And the medical evaluations for each of the programs were based on what was learned in the preceding program. Now, from Mercury through Apollo, we collected data on 34 astronauts, 19 flew one mission, and 15 flew multiple missions for a total of 59 manned missions.
Okay, I have to know what you learned.
So Project Mercury, a primary objective was to determine if humans could perform meaningful tasks well in space. There were 6 flights that lasted from 15 minutes to 34 hours. Now, there was no notable in-flight deterioration found in normal bodily functions, but there were multiple medical differences found during the post-flight medical exams compared to the pre-flight exams. Now, Project Mercury was unique in that there were multiple pre-flight simulations in the spacecraft, in the procedures trainer, and during centrifuge tests that were analogous in time to the space flights. Now, all Mercury crewmen had lost weight following all the flights, but also following the pre-flight simulations under normal gravity conditions. And this could be accounted for by a combination of a limited water intake and increased sweating while wearing a Mercury full pressure suit. And the cardiovascular changes that were noted included increased heart rate and decreased systolic blood pressure while sitting. And then there were significant increases in the heart rate and decreases in the blood pressure when changing to an upright position. Now, for the longest Mercury flight, the astronaut felt that he might faint when he first stood up.
Oh my goodness.
And this is known as orthostatic intolerance. Now, the post-flight changes were highly related to the weight loss. The overall data suggested that the weight loss and the subsequent changes in the cardiovascular system may be reduced by an in-flight replacement intake that included sufficient nutrients and fluid.
So, Bill, how did you build on that Mercury information as you went into Gemini?
Well, for the Gemini program, there were 10 flights that lasted from 5 hours to 14 days. And the objectives for this program included to subject 2 men to orbital spaceflight for up to 2 weeks duration. And this was the maximum time that was going to be required to complete a lunar landing mission. And then to gain additional information concerning the effects of weightlessness on the crewmen and to record their physiological reactions during and following the longer duration flights. Now, because of the findings in the Mercury astronauts, a pre-flight and post-flight tilt table test was added to evaluate the orthostatic tolerance. Now, this test involved a tilt table, lying flat on the tilt table, which was then tilted up to 70 degrees. Now, blood volumes were also measured in the 3 longest flights from 4 to 14 days using standard radioisotope techniques. And there was significant weight loss that was documented after all of the Gemini flights. The amount of weight loss varied between astronauts on the same flight and between measurements on the same crewmen on different flights of different durations. And there was a post-flight increase in plasma proteins and electrolytes, and this was consistent with the in-flight water and electrolyte loss. And then there was a retention of plasma electrolytes and a rapid weight gain post-flight that were consistent with recovery of the in-flight fluid loss. So the tilt test cardiovascular changes showed an increase in heart rate and decrease in systolic blood pressure that were directly related to the weight loss.
So what did you learn from the Apollo era?
Well, the Apollo program took place from September 1968 to December 1972. There were 11 Apollo flights with 3 crewmen per flight that varied from 6 to 12 days in duration. Now, the primary objective of the Apollo program was to land men on the moon and bring them back safely to Earth. Now, there were 6 flights with 12 crewmen that landed on the moon. Now, it was mandated that the crewmen for the first 3 moon landing flights would need to be quarantined for 3 weeks because of the remote possibility that there could be an organism on the moon that could be harmful to life on Earth. So extensive microbiological evaluations were developed. And the orthostatic tolerance test for Apollo used a lower body negative pressure device. And this device produced similar changes in the cardiovascular system that were seen from lying down to tilting upright in the Gemini program. And then I substituted a simple stand-up test when we were quarantined in the mobile quarantine trailer because of the space restrictions. Now, blood volumes were measured on 19 crewmen, and a pre- and post-flight exercise response test was added using a bicycle ergometer. And heart rate, blood pressure, workload, and oxygen consumption were recorded at multiple levels. And this data also provided important information for monitoring the crew when they were performing work tasks on the moon.
It's so important that we learn from that early Apollo data as to keep us moving forward, particularly as we look to our Artemis and Mars missions. The results of your integration can have implications for our private astronaut missions that we assist with now, as well as going back to the moon. So thank you for working on that. So Chuck, starting with Skylab, what were some of the more complex challenges related to human health and performance during your time with NASA? And then what did we learn? How did you resolve those challenges?
Skylab was the first NASA program, and I think to date the only one, where learning about human adaptation to space was the #1 priority. It consisted of 3 missions, approximately 1, 2, and 3 months each, with a crew of 3, because they used Apollo hardware, which was modified to support this program. For exercise, we learned the crews could maintain their body weight with appropriate nutrition, which is consistent with Dr. Carpentier's findings. We found crewmen could maintain and actually improve aerobic capacity given adequate exercise time and appropriate equipment. The cycloergometer was the primary exercise device, both for medical experiment M171 and for the crew in their personal exercise. As we went through the program, we flew additional pieces of equipment that were different ways of doing strength exercise as opposed to aerobic exercise. The good thing, too, about Skylab is medical privacy was not restricted. There was not the Privacy Act of 1974 because it hadn't been created. So we were able to openly plot each week's results and to sit there with the flight surgeons and with management and to discuss things in detail. And I think that was really important. And for years afterwards, it was difficult to do that. The Apollo-Soyuz test project came along in 1975. Most of you probably heard of it, but it was essentially a political science project in my mind, in that it was the first Russian-NASA collaboration on human spaceflight. The NASA commander was Tom Stafford, and post-flight, he led a working group with his Russian counterpart, Dr. Ushakov, that paved the way for NASA participation on the Mir station in the mid-90s, and actually Russian partnership on ISS. At the same time, most of you wouldn't know this, but the Russians had a biosatellite program. It was called Cosmos. And they opened it to US participation. And the first mission was in 1975. And my friend Ken Souza at NASA Ames Research Center led this activity that flew animal and plant experiments on 30-day missions on Russian biosatellites. The space shuttle came along after many years of patient waiting by most of us. And its challenge was that it landed like a high-speed glider. You got one pass at it and you had to be on target. This provided unique challenges for the pilots, particularly after the deconditioning of spaceflight. When flights were resumed following recovery from the Challenger accident, there were concerns about increasing flight durations from less than 7 days to approximately 18 days. And this led to creation of the Extended Duration Orbiter Medical Project, which ran from approximately 1989 to 95. EDOMP had the objective of safely increasing the shuttle flight duration, as I mentioned. We came up with some unique concepts that helped the crews in terms of being able to access them quickly after flight. One of the group had an idea to buy some of these commercial transport vehicles that were used at a few airports around the country and to modify it, which we did. We had one at Edwards and we had one at Kennedy, and we called them crew transport vehicles. But what we did is strip out all the seating and put in 7 big couches, one for each crewman, plus a separate medical examination area, where if there were something that had to be done critically, it could be done quickly and privately. I think quite a lot was accomplished in the 5 years of EDOMP. We had more than 30 hardware items developed and evaluated during that period. Many were prototypes of what eventually flew on space station. An example is the first treadmill. We also had this preliminary resistive exercise device, which had to be replaced by a later improved model. There were important flight rules that resulted from EDOMP, and flight rules are really key. One was mandatory fluid loading and mandatory G-suit inflation before reentry. A second was we added a liquid cooling garment to the pressure suit, and this greatly reduced overheating and instance of orthostatic intolerance, and also decreased post-flight nausea by more than 50%. Exercise became mandatory as a flight rule on flights exceeding 10 days in duration, and the idea was to exercise at least 3 times weekly, to a level for 20 minutes at approximately 60 to 80% of pre-flight max. And if this were done on the cyclogometer, we were able to maintain aerobic capacity within 6 to 12% of pre-flight values. Now, most investigators on EDOMP were NASA researchers because this was a highly schedule-driven operational program. This was expedient, but it resulted in considerable pushback from the extramural science community. In response, NASA determined that future flight programs would be more open to participation by extramural researchers. And one of the other things that led to was the foundation of the National Space Biomedical Research Institute, which we formed in 1997, and it was a 20-year cooperative agreement established with a consortium of 7 very prominent research universities. It was led by Bobby Alford at Baylor College of Medicine. The founding director was Larry Young from MIT, a well-known neuroscience investigator, and he was succeeded by Harvard's Jeffrey Sutton. Now, along the way, we had to do some programmatic things to help structure our program. And I think one of the real important ones was the creation of what we called at that time in 2000 or so, the Bioastronautics Critical Path Roadmap. It baselined about 55 risks and 250 research questions that were relevant to long-duration spaceflight. In 2002, NASA began to prioritize research for International Space Station. The roadmap itself is a systematic approach to prevent, control, eliminate, or reduce known risks to crew health, safety, and performance. It also provides good guidance for solicitation and selection of funded research. Most of this was summarized nicely by Jancy McPhee and John Charles in 2009 as the Human Health and Performance Risks of Space Exploration. And I think that publication is still very relevant today. I was able to have a little participation in some of the initial steps of International Space Station. But for those of you familiar with it, you know that it was primarily an assembly task for many, many flights, and we didn't have much research time per se. But in order to get ready for this, we had to create a vehicle for how we could approve human research in a safe manner. Basically, it's an IRB that was created with the international partners for Space Station. It's called the Human Research Multilateral Review Board. This board approves by consensus all human research to be performed on ISS. In 2015, we published a supplement in Aerospace Medicine and Human Performance Journal that summarizes the results of exercise countermeasures performed by the crews during expeditions 1 through 25. This unique document included results from a Russian team at the Institute of Biomedical Problems, Moscow, Russia. So I recommend it as a source of information about the early years on station.
Yeah, Chuck, thank you for sharing. And what I really like about listening to both Bill and you together is you can really see the evolution of complete unknowns. What's going to happen when someone comes out of this capsule, right? To starting to understand the problem, look at the challenges, and then also move towards countermeasures. So what interventions can we do to enable human spaceflight, particularly as we go to longer missions, particularly as we're like pushing what becomes the frontiers of human exploration. Dr. Joe Durbay, you are a current operational flight surgeon. And what I'd love to hear about is some of your experiences in both countermeasure development with different partners, as well as research operations working together, both in historical programs as well as our current programs.
Well, one in particular that we're very proud of from a life science community is the development of safe operational EVA pre-breathe protocols. These protocols are developed so that when crew members like Dr. Lindgren perform an EVA, they are in the safest postures they can to mitigate the risk of decompression sickness. All of us have approximately 1 liter of nitrogen in our systems, and as that gas could potentially evolve with pressure differentials, that could lead to things such as the bends that you've heard of with scuba divers. So we work to develop the scientific approach as to how we would physiologically get that gas out using some exercise and other aspects, but it is not a protocol that is developed strictly on a scientific realm. We have to work closely with the engineers, the suit technicians, the flight directors, and the crew to make sure that it's operationally relevant, that we can hit a certain timeline and keep them as safe as we can. And we've been very successful in that. It's probably been, in my estimate, one of the greatest gifts life sciences has been able to give to the ISS program, that we've developed 3 pre-breathe protocols. We have not had an account of decompression illness, and we've been able to build this, the station in a very nice way.
Yeah, it's amazing. It helped not only allow us to build the station, but I know that the research is now looking back at pre-breathe protocols for when we or looking to multiple EVAs onto the lunar surface.
And that's an excellent point. We do have work underway here at the Johnson Space Center looking at exploration of atmospheres, such as 8 pounds per square inch, 34% oxygen, and we're doing research trials on that. We'll be doing some more this spring, and looking to see if we can reduce the time it takes for pre-breathe and get crew members out the door quickly and efficiently and safely.
Yeah. I'd like to hear any additional contributions you can think of that really stood out to you.
Well, one thing we are tremendously proud of in the flight surgeon community is our support of the crew members. Learning from Dr. Carpentia's era throughout all the flight surgeons over the years, we've tried to develop the best relationship we can with the crew members, working closely with the behavioral health team, the crew support office to ensure that the crew members are taken care of, that their families are supported well. We typically are assigned to a mission a year and a half or so before. We work with the crew to ensure their training is going well, not only their medical training, supporting their simulations, attending some of their training at the Neutral Buoyancy Lab, and trying to develop that relationship that they trust us and that they can speak with us when they're on orbit. We communicate with them during a weekly private medical conference to discuss all aspects of their sleep, their circadian rhythm, their performance, their overall medical care and their exercise, and really try to work to maximize their health and performance.
And Joe, thank you for sharing about some of the medical support. We also have Dr. Al Holland, who leads the Behavioral Health and Performance Operational Group, and can tell us about some of the countermeasures that have been developed for behavioral health and performance, including the differences and changes over time with astronaut selection.
Over the years, one of the greatest steps forward is looking at the individual, not just the physiology, but stepping out and looking at the whole individual in the context of their family, in context of their relationship on board, in context with their relationship with ground, and moving into more of the psychological, the interpersonal, and the social aspects of the human system. I think that's been the most remarkable thing that I've seen. And it's been quite welcome. When I got here in 1984, I had this idea to put forward a selection program. And the selection program, so I went to the head of then Space and Life Sciences. And he was a venerable prior astronaut, well respected. And he sort of smiled and put his arm around me and said, "Son, you got to understand the crew won't be really satisfied until the last psychologist has been strangled on the entrails of the last flight surgeon." So that as a brand new psychologist at NASA, that put things in perspective for me. And I realized that there was some changes yet to come. But we did, with the advancement of long-duration spaceflight, which has been the real forcing factor here, we were able to put forward what we think are improvements in selection of astronauts and key personnel, as well as pre-flight training and gathering lessons learned from prior flights and passing them forward to new flyers, as well as in-flight support and keeping the connection warm between the crew member and the families, and in-flight monitoring. There have been a sequence of gradual improvements in those areas. And thanks to people who advocate in the crew office, such as Dr. Lindgren down there, it's hopefully will continue on, because we have a huge challenge ahead with sustained lunar operations and Mars in particularly. With the lack,
I was going to ask you about that. Can you speak a little bit to those changes that you see as we move to long duration and the different psychological supports and how they'll need to change or are changing?
Yeah, just from the operational point of view, because we have a whole research function in the behavioral health and performance area that's chewing away at these problems and bringing in some good data. But from the operational point of view, the communications lag is going to be, I think, one of the primary drivers for how we radically have to change the way we have been doing selection training, in-flight support, and in-flight monitoring. as well as the length of time, 2.5, 3 years per mission. So we will need to shift around and really need to look at the individual if we're going to sustain them, and the individual as a member of their family, and keep that connection warm and really push out on ways to keep the communication lines open and approach real time as much as possible. So that's a big part of it. And allow the crew to maintain some sort of community with a set of norms through their mission, so that when they re-enter back into the world they left, it won't be that different. It'll be a pretty smooth re-entry.
Right, because now we're talking about maybe 2.5-year missions someday and a 22-minute communication delay each way, which is just going to really
Huge.
Yeah. Make it important to have those different abilities to connect back with your families. And
Right.
so what about, I just wanted to ask you one last question about what you were saying. So a part of one of the most important countermeasures or way of making sure humans can succeed in space has been the selection of different individuals into the astronaut classes for training. What changes have you focused on as we look to more long duration flyers, particularly with the behavioral health and performance aspects?
Sure. Well, we have repeatedly, I'd say 3 times in the last 15 years, we've gone back to the mission. So we start with what's the target mission? What's the mission profile look like? And then we work from there with people who have flown missions similar to that in analog situations, in the polar stations or undersea stations or military units, and also flyers who have flown missions. By flyers, I mean astronauts who've flown missions approximating what we're looking at. And we'll take that sort of all that information together, and we'll define what competencies or attributes, skills that we're looking for in a person like that. So as we did last time, we worked very closely with a group of people within the astronaut office, and we established a sort of a sounding board panel. And as we developed information, they would process this information and bounce back to us and say what worked and what didn't work. And so we've gradually moved toward away from only the individual and looking only at the individual's ability to manage their own emotions, but also to look more at the interpersonal aspects, look at teamwork, look at leadership, and in particular followership. So there are a number of competencies that we've been able to develop in that manner. So I would say that's one thing. Another thing which I think has been a pretty good contribution has been looking at people not just from tests. You don't just give people a bunch of psych tests and say, okay, well, you want to be a forestry person, but you want to have a multi-method approach to that. So we do psychological testing, but we also do a very structured and targeted interview. We do behavioral exercises. We do peer ratings. We gather as much information as we can about an individual and in their context for these longer duration flights.
Well, it's also wonderful to have Vicki Claris here. You are just a fascinating person to talk to because you were the food manager for the shuttle and the ISS. And oftentimes, even when I go do outreach at schools talking about my own research, I always bring sample astronaut food so that the kids can experience, what it might be like to be an astronaut someday. Can you tell us about some of the contributions with the food program that you managed and kind of the different challenges that evolved over time?
Well, I think everyone is very aware of how important food and nutrition, diet and nutrition are to people's health here on the ground. And it's no different in space, and you have heard much of the data that's been discussed here has been relative to maintaining caloric intake, preventing weight loss because of the negative effects that has. So I came to work very early in the shuttle program. I think 16 of the 135 missions had flown. Rita Rapp was my NASA boss when I came to work here. And food was just not high on the priority list. I mean, I would say probably 98% of the shuttle astronauts that I worked with really took the attitude that a shuttle trip was a camping trip. They could find something they wanted. They'd come in, look at the menu, got to try things. And for a shuttle, the menu was 100% personal preference. So they would tell us what they wanted for each meal, and that worked great during the shuttle program because the crew member and the food were on the same vehicle, never got separated. So, but even with 100% personal preference, crew members they skipped a lot of meals on orbit. The flights were short, relatively in duration. Again, they most considered it a camping trip. And so they felt compelled to work all the time because they had so much to do and they knew they had a very limited time to do it in. And so we would get, on average, now this included, we sent a lot of reserve food too, if something happened and they couldn't land and had to orbit for additional days. But on average, we were getting around 70% of the food returned from flights. So it's not at all surprising that they were seeing weight loss and that was contributing. But that had a lot to do with the fact that they felt compelled to work all the time. As we got ready to go in the early 90s, when we were going to go send our folks to stay on Mir, I can remember the original plan was that there was going to be no NASA food sent to Mir. It was the crew members that went were going to eat all Russian food. Well, the late Dr. Charles Borland, who was managing the ISS food system at the time, the development of the ISS food system, he negotiated to get a small amount of NASA food on board Mir for those crew members who were going to go stay. And so I can remember talking to some of those first crew members and saying, what do you want to take? You know, it's going to be a limited amount. What do you want to take? And most of the response I got was, I'm busy learning about training for Mir. I'm busy learning Russian. Just go look at one of my shuttle menus from the past, because these were all people who'd flown before. Pick something off of there, it'll be fine. So that's what we did. And then post-flight, these folks who had now been up there long duration, at that time it was like 4.5 months. Yeah, something on that order. But most of them came back and said, oh, I should have paid more attention because psychologically the food became very important. And that's what the nutritional importance of the food hasn't really changed, other than we have learned more in partnership with the Nutritional Biochemistry Lab. We've learned more about the nutritional requirements and how they can be tweaked for space. For instance, we have reduced the sodium content in the food because we know that has an exacerbating effect on muscle loss and bone loss, and so that has changed over time. But basically, that nutritional aspect has been tweaked, but has remained the same. But that psychological aspect has really changed. And it was an educational thing for the crew office members as well, for the astronaut office to learn about the importance of the psychological aspect of food. We tried to continue the 100% personal preference menu into the space station era, and it was a disaster because we could not guarantee that the food that the crew member had selected would get there, all of it would get there at the appropriate time, because it was going on cargo vehicles, and those cargo vehicles would slip. And so it became a big psychological issue. We would hear in post-flight, you promised me the food that I requested, and part of the time I was up there, I had to eat somebody else's food, and they had terrible tasting food. And so when the first ESA unmanned cargo vehicle was going to fly, the management wanted to put a lot of clothing and a lot of food on it because it was an untried vehicle. And it kept slipping. The launch date for that kept slipping and slipping. So we knew there was going to be a lot of food on it. ESA wanted it about 9 months in advance of the flight because it had to go to South America to be launched. And so we knew. We had no idea who was going to be on board when that vehicle docked. So within the lab, our dietitian and our food science team, we came up with a standard menu and said, this is what we want to put. And basically that standard menu was designed to provide as much variety as the food system could provide. The wide variety was the most important thing. And so we presented that to the astronaut office. And much to my surprise, they said, not only do we want you to use that on that first flight, we want you to use that from now on, because we want to eliminate this psychological problem of eating somebody else's food. And so beginning with increment 16, we introduced the standard menu. And the agreement we made with the astronaut office was that we would provide some personal preference to augment that, but a smaller number of containers that we had a much better chance of getting there at the right time. And so now a lot of effort is put in to working with the crew members for their preference containers, because we know psychologically how important that is to have that reminder of home, that personal thing that you like the best in the food system.
And Vicki, I can personally confirm that, I think we all recognize the nutritional benefit of the food. Our flight surgeons are constantly hounding our caloric intake to make sure that we're providing enough nutrition to support the exercise that we're doing, that we're not going to lose body weight, that we're supporting our bone health and muscle health. But the psychological benefit, on the ground we use food not only for nutrition, but to celebrate, to commiserate. And so a lot of that gathering, that bonding with the crew is done around food. We'll take the food and so, for example, during our flight, Jessica Watkins had a birthday within days of us arriving on flight, and we took various pieces from the pantry and made a birthday cake for her. And so those are super important things. When you're kind of having a bad day, a coffee and I'm trying to think of something, maybe some cookies, go a long way to kind of cheering you up.
So Vicki, could you just speak just briefly to some of the challenges you're talking about, the opportunities and the evolution of what's happened with food will be more complicated tenfold in something like a mission to Mars. Can you tell us a little bit about what's happening in the research world at NASA for that right now?
So the biggest challenge for a mission to Mars is the fact that the type of shelf life that's going to be needed for especially that food on the first mission. Because we know that just the logistics of getting to Mars, it's long, it's drawn out. And we're going to have to pre-position supplies and verify that they're there before we can launch crew members. And so what that means is that the food that the crew eats on that return trip, that first return trip, could be 5 years or more in age. Now, we can produce food from a microbiological perspective that's safe to eat for that length of time. But the thing, and because we can, by processing the food to shelf stability, we can control microbial growth. What we cannot stop is the chemical changes that occur within that food. And so those chemical changes are going to reduce the acceptability of that food because they alter the color, the flavor, the texture over time, and they alter the nutritional content. So there are certain nutrients that are more susceptible to that kind of degradation over time. So the challenge is to find out, how many foods can we have that will have adequate shelf life, will maintain nutritional content over that length of time? How much variety do you really need to support a crew, for them, from a psychological perspective, because a lot of us are pretty redundant in what we eat every day, but then some of us aren't. And so it's going to be hard to find that happy medium of how much variety do we need. And, so that's a big challenge, but that's that's the focus of the research that's going on in the food area now, is looking at what nutrients degrade, what qualities of food degrade, how can we control and try to control those chemical degradations in the food, and how much variety do we need to support a crew on a Mars mission.
And I think one of the really exciting things that we were doing on station, and I got to do this during my first mission, as well as this most recent mission, is looking at the viability of being able to grow food during the mission. And so we have an enclosure. It was called Veggie the first time I flew. This time it was called X-Roots. But we had the opportunity to grow edible crops. During my first mission, we were the first crew to grow red romaine lettuce and to get to officially get to eat it. And then this most recent mission, so during that first mission, those were grown in pillows of a soil matrix. So imagine kind of a bean bag and then a plant growing out of that the bean bag, the soil within that bean bag providing a matrix for the roots. And during this most recent mission, X-Roots, we were looking at hydroponics and aeroponics as a potential methodology for supporting plant growth. We grew beans, peas, carrots, radishes, so again, edible crops. And I think it's really exciting because there's a possibility. I think if we're able to scale these up, I imagine a module, I've seen it in science fiction movies, but I imagine a module that is the farm or the greenhouse, where it's just a module that's filled with growing plants. And so for myself, when I got to take care of the plants, I think all of us would go in there, would pull down the enclosure and just kind of stick our head right next to the enclosure, because that smell of, it's essentially earth. It's the smell of earth to smell these growing plants. And so I know our whole crew enjoyed taking care of those plants, because it is one, we live in this fairly sterile environment of station, and to see something that is growing every day, to see that green color in kind of the silver and white of space station, there's a psychological benefit in addition to that potential future nutritional benefit. Millions of gardeners all over the earth can't be wrong. And so that psychological benefit of taking care of something on a daily basis, I think, is very powerful. And then I think, potentially if we can build a resilient crop system, it's something that can contribute to our environmental control system, pulling carbon dioxide out of the air. So I think that research was really exciting and a powerful adjunct to the research that your lab is doing.
Absolutely.
Yeah, thank you very much. Chell, we loved hearing about the Veggie experiment that you participated in, and there's so many other things that you're a consumer of as the astronaut that the huge human health and performance team is really trying to support, whether through research or operations. Can you touch on any of the other contributions that you've really felt or experienced as a crew member, and what those have either meant for you or where you can see opportunities and challenges that need to be addressed?
Sure. Well, thank you. I guess I really want to just first start out and really kind of identify what a rare privilege it is to be a part of this panel. So for those in the audience that have been here for a long time, you recognize this, but I think I see newer faces in the audience, and and for the folks that are watching online, what a rare opportunity is to have the breadth of space, the support for human spaceflight, health and human performance, space medicine represented on the stage here. To have the perspective and experience reaching all the way back to the very beginning of our space program is an incredible thing. I've wanted to be an astronaut for as long as I can remember. I thought that the path was through engineering. I quickly discovered an aversion to Calculus 3 and a joy in biology. And so I switched my major to biology and pre-medicine. But with that passion about science, I was deeply, deeply interested in space medicine and reading papers written by Drs. Carpentier and Dr. Sawin. I did my senior thesis on orthostatic intolerance, and so what a privilege it is to be sitting on this stage with this team that inspired me, and then parts of the team that directly supported my missions and then the missions of crew members on the space station now. I was Dr. Dervay's deputy surgeon for STS-24. I ditched him for a job in the astronaut office. I apologize for that, Dr. Dervay. But have the privilege, he was my crew surgeon for this most recent mission. Dr. Holland was my BHP operational psychologist for this mission, and I've worked with Vicki over the years in selecting food. The astronauts that went on Mir complained that they did not spend enough time really thinking about their menu. As a veteran astronaut preparing for my second mission, I still did not spend enough time choosing out the very specific things that I wanted in my crew-specific menu. So I just continue to make those mistakes, and it's something that I get to complain about, though. So, but I look at what we're doing on the International Space Station. Over 20 years of continuous human presence in low Earth orbit. So that is an absolutely amazing thing. I think about it as an intricate tapestry that we have created, that we have woven together over those 20 years. And if you look at this panel, you see threads of that tapestry reaching back to individuals on this panel. So when we think about Mercury, Mercury, we were just figuring out, could we survive in space? I remember reading early papers that one of the concerns is, could we swallow in space? Could we drink water and eat food? That was a question. And our Mercury researchers and flight surgeons helped us answer that question. We could survive in space very successfully. And then we went on to ask, can we do valuable work in space? Can we actually get things done? That was what the Gemini program that Dr. Carpentier supported, that was what he was looking at. We had to figure out, could we do the things that we needed to do to get to the moon? Could we do EVA, extravehicular activity, spacewalks, to do repairs, to go outside, to do the exploration on the moon? Could we do rendezvous, bring vehicles together? Specifically for Apollo, could we dock the Apollo capsule ultimately with the lunar module? And so we practiced that during Gemini, bringing the Gemini capsule and docking it with the Agena rockets. Could we fly in formation? Could we rendezvous? Those are all questions. And so when I think about Gemini and long duration experiences, I spent 8 hours in a Soyuz capsule. And it's something that I'll share with people and say, man, this was tough work. Look at what I accomplished. Knees to my chest in a Gemini capsule, or I'm sorry, in a Soyuz for 8 hours. For the last Gemini mission, you had 2 astronauts sitting in the equivalent of the front of a VW Bug for 2 weeks. It is mind-boggling to me that they were able to pull that off. And so I have so many questions for you about that and just the concerns that we had for the astronauts that we're going to try and pull that off. It's incomprehensible to me. But that laid the foundation not only for Apollo, but for 2-week missions on the space shuttle. And then on to Apollo. So those threads of just surviving and doing work in space, doing our first spacewalks, extend to what we do on the space station. And then on to Apollo and the amazing things that we accomplished with Apollo, and then on to Skylab, our very first space station, where we proved that we could match the Russians, that we could do long-duration space flight. With the, I love to say it, SMEAT, the Skylab medical experiments altitude test, to determine could we operate and conduct experiments in that atmosphere, and then with Skylab with long-duration missions. Those were our first long-duration astronauts, and it's lessons from Skylab that we, again, pulled into the space station program. These were the first astronauts to do long-duration mission and to return to Earth deconditioned in a capsule and land on water. I personally benefited from that. I did a long duration mission and returned to Earth in a capsule and landing on water. And all of the concerns that we had with that, how's a deconditioned astronaut going to react to floating on water? What are our escape possibilities? Do we want to let deconditioned astronauts or crew members get into the water in the event that the capsule is sinking? Those are all things that we had to consider. And as a flight surgeon, we actually leaned on the Skylab crew. We brought them here for a conference to lean on their experience, to feed that directly into what we were doing ultimately with Space Station and Orion. And so you can see the contributions that these programs ultimately led to Space Station. And then after Skylab, Apollo-Soyuz, I mean, is the origins of the origin story, if you will, of our relationship with the Russians. That first kind of crack in the Cold War, in the wall, the beginning of cooperation that has led to what we are doing right now. And what I think is one of the absolute fundamental benefits of the International Space Station program is that international partnership, the cooperation and collaboration that we have with not only the Russians, but with all of our international partners working together for an amazing, peaceful project that is bigger than all of us. When you think about that International Space Station, what we are accomplishing together with nations that just 40, 50, 60 years ago were mortal enemies, what we have accomplished together now is absolutely incredible. And so the Apollo-Soyuz test project was the origin story for that relationship. The Prophylactorium, the Prophy, is a building that my understanding was built to house the Skylab astronauts. Is that true?
I'm sorry, building?
The Prophylactorium, the Prophy?
I don't.
They're on Skylab? Okay. So my understanding is that was where Stafford and Slayton and that crew all stayed while they were there in Star City. And that's a building that we still use today. Our NASA office is housed in that building. When I was a flight surgeon supporting the space station crew in Star City, that's where I had my little medical office, and it's where I stayed, and that's where our flight surgeons still stay today. So Apollo-Soyuz test project, and then the shuttle program, obviously. So again, was a huge part of weaving that space station tapestry. It is what built Station. It hauled Station up there, and what an absolutely amazing vehicle it is. We conducted spacewalks from Station. Shuttle crews conducted spacewalks from the Station airlock to construct this absolutely magnificent structure that we now have in space. And then Shuttle Mir, our very first opportunity to put crew members on the Mir, for them to work in that environment, to train with the Russians, and to live and work in that environment as we prepared to undertake Space Station itself as a team. And so, again, an incredible privilege for me, getting to pursue medicine, to find a place in human space flight as a physician, to do a residency down in Galveston in aerospace medicine, and then to have the great fortune to get a job here at NASA as a flight surgeon, following in the footsteps of many of the panelists we have today here today, and then the incredible core of folks that we have still supporting. But then to go on and have the rare opportunity to serve as a crew member. Very grateful for that, and to be a beneficiary of all the incredible work that has been done for that critical element of spaceflight, and that is humans. This is human space flight, and we absolutely could not survive, much less thrive, without the contributions of the folks here on the stage today, of many of you in the audience, and many of you that are watching online. I think sometimes as we think about what we do, we think about the rockets, we think about the technology, the rocket engines, the boosters, all of those things. The hardware is incredibly impressive. But it is that human element that we strive to protect. And as I know oftentimes a pain in the butt. But I know that I speak for the crew office when we thank you for all of the work that you do to make what we do possible. So space station operations, I've had the opportunity to fly, as Suzanne mentioned, 311 days over 2 missions, and supported directly by, from a medical standpoint, and I put Dr. DeVay to work this time around. The incredible work that our behavioral health folks, the operational psychologists and operational support that is provided to us, making long duration space flight possible. The ability to communicate with our families over a voice over internet protocol phone. Absolutely mind-blowing that I can dial from my laptop computer on the space station any number on the ground and talk to somebody on a line that is clearer than my cell phone is here on the Earth. To share that experience, to maintain that connection that we have with families. That is human space, that's the human part of space flight. That we're able to connect over video conferencing software, and that I'm able to spend time with my family, an hour and a half, seeing my family and talking with my family once a week. That supports that human element of human space flight. And then the incredible amount of personal stuff that we get to bring with us and that comes up in space, in care packages. Again, that makes these long duration missions incredibly tolerable, so that we're not just surviving, that we are able to really not, if you think about Maslow's hierarchy, we're really well taken care of, so that we can reach that point where we're focused on the job and able to do the things that the program is set up there to do the science and research that improves life here back on Earth and extends our presence in the solar system. So in the end, that tapestry that we're weaving together, I think, really supports this idea that that space flight is truly the ultimate team sport. That it takes a community like this to support humans in space. All of the contributions that you all have made to directly support that small part of the crew, those few people that get to actually ride on that rocket and spend time in low Earth orbit. This team and the wider team, the engineers, the scientists here at JSC, at all of our centers, and with our partners all over the world to make this happen. We've been doing Space Station now for over 22 years, and I look forward to the future that we have on station to continue to conduct that research to enable our exploration of the moon and Mars, and really just a privilege to be a part of it with this team.
Yeah. Well, thank you. It's been an absolute inspiration listening to all of you today. Thank you so very much for your time, and it's a real gift that we've been able to talk with you today. Thank you for inspiring us to move from the unknown to the known, and how we've faced evolving and different challenges over time as mission goals change and as the nature of missions changes. We're inspired by what we hear today. How teamwork, different perspectives and approaches can be used to solving the challenges of human adaptation to spaceflight, and the importance of partnership between research and operations and research, constantly informing one another so that humans can survive and thrive in the extreme conditions of spaceflight. That's going to wrap up our panel for today. And as we close, after closing, if the panelists would like to stay for a little bit of questions and answers from our audience here today. But again, thank you so much for your time today. It's a true gift.